Hi everyone, welcome back to another video on problem solving session. Today we're going to look at a problem called a uniform ladder, and it is on the A-level IB and leaving cert or other high school syllabus, and it's ranked as 2 C's out of 3 C's, which means it is a very difficult problem. It could be quite useful if you're preparing for, let's say, academic Olympiads, or just, out there trying to solve some difficult problems. So here we go. Let's read the problem. The uniform ladder AB of mass M rests in equilibrium. A is in contact with the smooth vertical wall, and B is in contact with the rough horizontal floor. The ladder lies in a vertical plane, perpendicular to the wall, and makes an acute angle alpha to the horizontal. A horizontal force P is applied to the ladder, direction away from the perpendicular to the wall. This force acts at the point 1/4 of the way up the ladder. We will have questions given to us, but we first need to draw the diagram out. So essentially what we have is this setup here, where there's a floor and a 90 degrees door, and there is the ladder here. So A is this position, B is here, and B's okay. So a ladder lies in vertical plane, blah blah blah. So this acute angle is alpha here, and horizontal force P is applied to the ladder in a direction away from the perpendicular walls, so 1/4 up. Okay, so it's like this. So there is a force acting as such, P. Okay, so let's look at part A of the problem. So part A is find in terms of the magnitude of the normal reaction force at B. So find NB, and NB is here. We're given that this wall is smooth. Let's just draw the forces out. So if wall A is smooth, that means there is no frictional force acting on wall A, and therefore we'd conclude that MB is equal to MG. And let's check the answer, MG. It is correct. Yeah, this is largely correct, and actually there is a resistive force here too, just to complete the diagram. I'm just going to have a look at the solution video, what they say.
The ladder is in equilibrium, so the resultant force on it must be zero. Hence, we can find NB simply by considering vertically acting forces.
Okay, so I was correct. Now, part B is find in terms of P, M, and alpha the magnitude of the normal reaction force at A and A. So find NA. So essentially, here what we need to do is take torques clockwise and anti-clockwise, and they must be balanced. Torques at B. So the clockwise torques are NA times let's say the length of the ladder is L. Say this is L, and so the clockwise torques would be NA, the normal force, times L sine alpha, sorry, that's alpha not theta. Yeah, L sine alpha, yeah, and yeah, that's right. And anti-clockwise, and plus p times L, a quarter of L, times, what is it? Yes, sine alpha. And the anti-clockwise is just mg times L over 2 of cos alpha. And equating those two expressions, we get Na times sine alpha, and also cancelling out the L's, plus P over 4 sine of alpha is equal to mg over 2 cosine of alpha. So moving things to the we can divide both sides by cos of alpha, so we get Na tangent of alpha plus p over 4 tangent of alpha is equal to mg over 2. So Na tan alpha is equal to mg over 2 minus p over 4 tan alpha, and so Na is equal to mg over 2 tan alpha minus p over 4, and we're going to see if that's the correct answer. So I'm just going to key in the expression mg divided by, so brackets mg divided by 2 times tangent of alpha minus p over 4. Yes, that is correct. So it says, what is the goal of the question? Well, the goal is to find Na, what is the key information given, blah, blah, blah. Hint 2, draw a diagram. So that's the diagram. Hint 3, what concepts are relevant. Hint 4, what equations are relevant. And hint 5 is the answer. Let's watch the answer on IsaacPhysics.
The standing on a rough floor leans against a smooth wall. The ladder is at an angle alpha to the horizontal. Forces on the ladder are a normal reaction force at the wall, Na, a normal reaction force at the floor, Nb, the ladder's weight, mg, acting at its center, the force P which is being applied a quarter of the way up, and the frictional force at the floor, Fr. The ladder has length L. We can find Na without having to worry about the normal reaction and the frictional force at point B by taking moments around point B. As the ladder is in equilibrium, the total of the clockwise moments around this point must equal the total of the anti-clockwise moments around this point. Be careful when calculating the moment due to each force to make sure that you use the correct angle.
Okay, so essentially the official solution is exactly the same as mine, and we can move on to part C. So part C, you're asked to find the magnitude of the friction force on the ladder at B. So essentially you're asked to find Fr. So here what you can do, you can essentially resolve the forces, resolve the torques at point A. So resolve torques at A. How you do that is say, well, clockwise, let's see what are the clockwise torques. So clockwise is Fr times L sine of alpha. So Fr times L sine of alpha plus what else? Plus mg over 2 sine of alpha, mg L over 2 sine of alpha. What else do we have? Yeah, I think that's probably it. then we need to resolve anti-clockwise. Anti-clockwise, we have the anti-clockwise forces are the normal force at B and P. So normal force at B is NB, which is also we've proved earlier in part A is equal to mg. So that's mg times L cosine of alpha. So mgl cos alpha plus what else here? So P is the force, but the distance to A is I think P times the torque would be equal to P times 3L over 4 times sine of alpha. Yeah, it's 3P times 3L over 4 times sine of alpha. So equating those two expressions and getting rid of L, length of the ladder on both sides, we get FR times sine of alpha plus mg over 2 sine of alpha is equal to mg cosine of alpha plus p times 3 over 4 sine of alpha. And next step is to divide expressions by sine of alpha. We have FR plus mg over 2 plus mg over tangent of theta of alpha plus 3p over 4, and that's equal. So FR, the resistant forces, is equal to mg 1 over tan of alpha minus a half plus 3p over 4, and I think that is the answer. Or you can alternatively write mg of cot alpha minus half plus 3p over 4. Let's check the answer. So mg of cotangent. Oh, we're not allowed to use cotangent, so let's go with this. 1 over tangent of alpha minus a half plus 3p over 4. Okay, so plus 3p over 4. Incorrect. It says it is incorrect. Let's review the question again. It says find the magnitude of the frictional force on the ladder at B. So essentially we're finding the resistive force at B. Yeah, so the resistive force times the L sine of alpha, we have that, plus mg, yeah, times L over 2 of cosine alpha, yeah. Oh, it's not. Oh yeah, I see where the problem is, because it should have been cosine of alpha here. I've been very incautious. This should be cosine of alpha. So this was cosine of alpha, and if you divide by, actually it would have been a lot easier if I had used I'd divided both sides by cosine of alpha instead of sine of alpha. So dividing both sides by cosine of alpha, you have FR tangent of alpha plus mg over 2 is equal to mg plus 3p over 4 tangent of alpha. Then you get FR is tangent of alpha is equal to mg over 2 plus 3p over 4 tangent of alpha. And then you get FR is equal to mg divided by 2 tangent alpha plus 3p over 4. Let's key in that to the equation again just to check. So you have mg divided by 2 tangent of alpha, and then plus 3p over 4, and that is correct. So let's have a look at what the IsaacPhysics official solution is like.
As the ladder is in equilibrium, the horizontal forces must balance. Resolving horizontally, this gives us that Na plus P equals Fr.
Okay. So part D. Question asks, if the coefficient of friction between the ladder and the floor at B is mu, if mu is equal to cotangent of alpha, and the value of P is gradually increased from 0, how will the equilibrium be broken? Okay, so if the coefficient of friction is cotangent of alpha, if and P increases from 0, how will the equilibrium be broken? Well, this is something to think about. So let's go back to the diagram here. So we know that already the resistive force is equal to a chunk, mg over 2 cotangent of theta plus 3p over 4. And that is the maximum force, right? So if you think about it, we know that Fr is equal to mg over 2 cotangent of alpha plus 3p over 4, and that's equal to mu mg, and we're given that mu is cotan of alpha, so that's equal to mg cotan of alpha. So we get 3p over 4 is equal to mg over 2 cotan of alpha. So yeah. So essentially what happens is okay, so it says if P is gradually increased from 0, so let's tidy up the expressions a bit more. 2mg, so 2mg over 3 cotan of alpha. 2mg over 3 can't change, but cotan of alpha can. So cotan of alpha is equal to 1 over tan of alpha. We know that tan of alpha is like this. So cotan of alpha would look something like this. It's decreasing, cotan of alpha, as alpha increases. So, okay. So if P increases, cotan of alpha would increase, and alpha would decrease. So I think we would slide, yeah. So the equilibrium would be broken by the ladder sliding. Okay, let's look at the hints given and the answer for this question by IsaacPhysics.
On the point of toppling, Na equals 0. So by taking moments about point B, we can find the magnitude of P that would cause the ladder to topple. From this, we should be able to find the critical value of mu, which, if exceeded, would cause toppling.
Next question, part E. Let's move on to part E. Next question is, if the coefficient of friction between the ladder and the floor B is mu equals to 4, if mu is equal to 4 cotangent of alpha, there, and the value of P is gradually increased from 0, how will the equilibrium be broken? So we know that F res is equal to mg over 2 cotan of alpha plus 3p over 4, and that's equal to mu mg, which is 4 mu mg, which is 4 cotan alpha mg. So we get 3p over 4 is equal to 7 over 2, is that right? Mg cotan of alpha. And so we have 3p is equal to 14, so p is equal to 14 over 3 mg cotan of alpha. And so what this means is, okay, I think it means that it will topple, yeah, because the coefficient of friction is greater than the critical coefficient. So if it's greater than critical value, then this whole thing will topple, essentially. Yeah.